Okay, 1994, AB1. Let f be the function given by f of x is 3x to the fourth plus x to the third minus 21x squared. Write an equation of the line tangent to the graph of f at the point 2 and negative 28. So obviously, to find the equation of a tangent line, we need the slope, the point slope form of a linear equation, and so we need a point and a slope. The point is given to us at 2 and negative 28, and the slope is just going to be the value of the derivative of f when x is equal to 2. And so we end up with 12x to the third plus 3x squared minus 42x. Now we don't need that at this particular point, but I'm going to go ahead and factor. And I bring out a 3x, and I had 3x times the quantity 4x squared plus x minus 14. And so I'm looking for two numbers that multiply to give me negative 56, but add to give me 1. And those two numbers should be 8 and negative 7. And so I use 8 and negative 7 to rewrite the middle term x, and I get 8x minus 7x. And then I'm going to use factor by grouping. Sorry, that should have been a 14 at the end. And that should have also been negative 14 at the end previous to that. So it's 3x times the quantity 4x times x plus 2 minus 7 times x plus 2. And so we get 3x times the quantity 4x minus 7 times the quantity x plus 2 is the way we're going to factor that. Now that was a lot of factoring. We don't particularly need that for here, but you'll see in the factored form how much easier this calculation becomes. What we're trying to find now is f prime of 2. Well, 3 times 2 is 6. 4 times 2 is 8 minus 7 is 1. And 2 plus 2 is 4. And that value is 24. Now we did a little extra work to get that, but we're going to need to do that factoring anyway later on. And it would have been much more complicated to plug 2 into 12x to the third plus 3x squared minus 42x than it was to get the simple values that we got here. And so our final answer is y minus negative 28, or y plus 28, is equal to 24 times the quantity x minus 2. Part B, find the absolute minimum value of f. First important thing to note here is that we are not working with a closed interval, so we're not guaranteed to have an absolute minimum value of f. There may be one, but we're not guaranteed it. Now, how would we know that there is, in fact, an absolute minimum value of x? We know that from the fact that this is a fourth degree polynomial function. And a fourth degree polynomial function, at its most craziness, has a W shape to it. Perhaps something like that. The two vertices of those bottom parts there might be at the same level, and they might not be. One might dip a little bit lower than the other one. So since we don't have a closed interval, we don't need to worry about the endpoints here. And we're looking for which of those relative minimums are lower. And so we know that the relative minimums occur at critical points. And so all we have to do is find the critical points and then test their values back into the original function. Now fortunately, and we did all this work already, we have already factored the original function, the first derivative. We factored it to be 3x times the quantity 4x minus 7 times the quantity x plus 2, and that will be 0 at x equals 0, x equals 7 over 4, and x equals negative 2. So what we need to do now is to test the original function at those three values and determine which of them have the lowest points. Now just by knowing the fourth degree function, you would know that two of those values are minimums and one of them is a maximum. So x equals negative 2, so we have x equals negative 2 and x equals 7/4 have to be minimums, but x equals 0 is going to be a relative maximum. It's enough to use that kind of reasoning to save yourself the time of trying to evaluate x of 0. Although that is the easiest one, it happens to be 0. When we plug back into the original function, we're going to get a 0 there. Now I tried to factor the original function and it didn't seem to give me a nice factoring there. So in the next video I'm going to show you how I would go about evaluating these points.